All right, so welcome once again. And our first session is going to be just a brief info session on IEEE and what IEEE is all about. Okay, yeah, so you guys can see my screen. And how EUV lithography is powering modern chips and your gateway into that industry. Once again, my name is Chukwudi Ebubeyanene. I am the chair of IEEE in ATBU, the IEEE Student Branch in ATBU. I've actually graduated, but I am still interim chair for now. Yeah, so I'm going to just be discussing a bit on um, IEEE and what it really is for you as a student, if you are, and even a graduate. So IEEE was started in 1884 by some group of engineers in US, and over the years it has evolved. I'm going to be very brief because we've wasted some time. And so now IEEE is synonymous with technology and innovation. Um, it's now a house brand, like it's all over the world. It's well known. Um, it stands for everything about technology, from mechanical to electrical, whatsoever engineering, whatsoever technology. IEEE is like the leading organization of that, and it's the largest organization in the world, technical organization in the world. Um, so we are a student branch within ATBU. Student branches are located across the world, across universities and colleges and any place of higher education. So we have a student branch in ATBU, and these are just a few things that we do as a student branch. Yeah, so IEEE has some extras. You have access to some various other things within IEEE. So, for instance, the special interest groups. Special interest groups are parts of IEEE that deal with um, things that are not, we won't say technologically technology per se, but um, some kind of social social work. So, for instance, women in engineering, young professionals, IEEE young professionals, sites special interest group on humanitarian technology. There are also others, and these are just basically what they do. Just a few of them. Um, then we have the technical societies. IEEE has about 39 of them. Basically, what they do is to help push the technological advancements of the world, right? So advancing technology for humanity. That these 39 societies are basically the ones that are like the foundation that hold technology advancements of IEEE, and they're quite a number here. And we have the EMBS, Engineering, Medicine and Biology Society, we have Computer Society, and a lot more. Then in the student branch and in IEEE in general, you can volunteer. Please, if you can't hear me, just indicate. Okay. So, volunteering is very worth it in IEEE. There's different ways to volunteer, right? So, for instance, these four. So you can volunteer by we have what they call pre-university outreaches. So this is where university students or college students go to pre-university, so that's secondary schools, primary schools, and try to evangelize engineering and technology to those students. We also have community services, outreaches. So, for instance, IEEE can sponsor a technological service to a community, maybe setting up a solar powered um, pump for water, or anything that has to help a community via technology. And then we have student branch, so you can volunteer within your student branch. So, for instance, this is my student branch in ATB, right? Then um, you cannot volunteer in the section. Why is it divided into sections? Because it's divided into sections, region, and some other geographical units. So you can also volunteer in the section, like in the Nigeria section, maybe as if you are someone that is good with web, you can volunteer as a webmaster for one of the conferences or stuff like that. So these are just various ways of volunteering. And the most important thing, a lot of people ask me this question, um, and like when I'm reaching out to people, they ask, I mean, what do they gain in IEEE? They are not electrical engineering students, so what are they gaining? But the scope of IEEE is very broad, and these are just a few. As far as you are a professional or a student in one of these fields, you qualify to be an IEEE member, and is this is a reason why a lot of people don't really want to join, because they feel they don't have um, they don't have that need to join. But yeah, as far as you are a professional and a student of either of these, you actually are able to join IEEE. So yeah, since we are a student gathering, I am going to be kind of theme of what you gain as a student, right? So basically, you have the ability to travel a lot of places. So at least in your time as a student, in your 5, 6, or if you are pursuing graduate studies, to in your, let's say, 10-year period as a student, have the ability to travel to different countries, and they are all sponsored by IEEE, right? So, for instance, the EMBC, so that's the flagship conference of engineering, medicine, and biology. They had their travel grants applications earlier this year. It has ended actually, but this is one of the big opportunities for traveling. Of course, this some of these opportunities require that you write papers. Some require that you are contesting, so through hardware or software contests, and some, like the shirt design contest, are just basically you having your creative design, coming up with creative design and submitting. So, for instance, this one is open. This is from the Solid State Circuit Society, the one on top. So the shirt design contest is open for now. It's ending in September. Yeah, September 25. So basically, it's just you coming up with a design for their conference shirts, and if your design is chosen, you win $1,000, and you also get to travel for one of the conferences. Right. So this is something you can gain. Um, then there are also scholarships and fellowships, and recognitions, kind of. So I just listed a few that I know Nigerians that have won personally. I know from the Signal Processing Society, from NTTS, from Electron Devices Society, from AESS, Aerospace and Electronic Systems Society. These are just a few of them. Nigerians have won more others from other societies too. Um, I mean, the highest I've seen was $10,000, and that was this year from someone from OAU. We also have, like, I won last year, the Electron Devices Society. That's just my plaque that I put as a picture there. Um, One of our students also won $5,000 from Systems Council, right? So these are very big opportunities for you to gain recognition, right, from IEEE. And you should know that these things are global. So once you gain one of these stuff, you kind of have some kind of reputation, right? So yeah. So my appeal is for those who aren't IEEE members yet. It's very important that you join the community, join IEEE wherever you are. You don't even have to be TBU. Just figure out, look for the parts, your niche, and then look for which societies, which affinity groups, which parts of IEEE interests you and join. For now, IEEE has yeah, so they're doing what they call half yearly payments. I think it ends in September. So you pay half of what it usually is for your, yeah, what it usually is. So it's I think right now is at $7 for undergrad and $14 for graduate members. And yeah, I'm done with my small info session on IEEE. So if you have any questions of about IEEE, you can just also let me know. Uh, yeah. So I think with that, I will invite our guest speaker to. But before he comes up, I'll just read his bio. Let me quickly read his bio. So, like I said, our moderator is actually struggling with her network. I don't know if she's back. Deborah, do you think you can take up, or I should just continue? All right, so let me read uh, the bio of sorry. Okay. So I hope you guys can hear me properly. Someone said it's cracking. I don't know. I think you guys can hear me properly. All right. So let me read the bio. Adewale Ifeoluwa Adejimi is a CS Extreme Ultraviolet as EUV competence engineer at ASML in USC with a background in advanced optics, photonics research, and semiconductor manufacturing. His journey spans education in Nigeria and graduate studies in Germany under the Abe School of Photonics Scholarship and hands-on engineering with lithography innovation. He is a leader in the sorry with the lithography innovation leader in semiconductor industry where he works at the intersection. I think that's typo there. At the intersection of high precision lithography systems, field service excellence, and technical problem solving. Beyond his technical work, he is passionate about lifelong learning, mentoring underrepresented students, and sharing insights on careers in optics and engineering. So, without further ado, I would like to welcome our guest to take up his session. Mr. Wale, yeah, up to you.
Can you hear me, sir?
Yes, I can hear you. I
Yeah.
believe everyone else can.
Can you also see my screen?
Please, if you can, not yet.
You don't see my screen?
No.
I'm sharing. It shows I'm sharing already.
Uh,
You,
not
you,
yet.
you you cannot see it now.
No, we can't see it.
Let me
Yeah, I've
stop.
stopped sharing some. Let me see. Hold on.
Oh, you were sharing before. Let me
Yes, let
let
me
me
let me see if it's still what is causing. Okay. So I've stopped sharing.
and now
Oh, my screen is still showing.
you still don't see my screen.
No, not yet. They're saying my screen is still showing, so I'm trying to figure out why. Is it still showing? Is my screen still showing?
I stopped sharing, so I have to do it
Ah,
again. Let me try
okay.
again. So now I want to start to share again. Let's see. What of now? Do you see my screen? It shows here that I'm
Okay.
sharing
Yeah.
the
Yeah. Yeah.
window.
Yeah. Yeah. Okay. Yeah. So I see. I see. What's the issue? It's showing. There are two options where my this is. So it's I can see your screen now. It's blue, right? How EUV.
Yeah.
Yeah, you can see it.
Can
I
everybody
hope
see
others
it?
can see.
Can we have some confirmation?
Okay.
Let
Yeah.
me let
So everyone can see.
Okay, okay. Yeah, so just because I
Yeah.
can only
Yeah.
see my
Everyone
screen,
is seeing.
so yeah, if there's any disconnection or something, let me know. Just speak up because I cannot see anything on the screen. I'm only seeing my screen, so I will only speak to the slide. So
All
if there
right.
are any issues, just speak up, then
All
I will
right.
know there's something wrong. Yeah, so thank you for invitation.
Okay.
Thank you for inviting me to this session. Good afternoon, everyone in Nigeria and whoever is in Europe, good afternoon, and in US, it's still good morning for us. It's still 10 o'clock in the morning. Uh, I'm glad to be here, and it's a privilege to speak with you today on the topic how EUV lithography powers modern chips, a practical roadmap into the semiconductor industry. I'm Adewale Adejimi, CS Competence Engineer in ASML USA. And Yeah, let's dive into it. So, some more personal introduction. I know the host has shared some stuff about me earlier. So, some more stuff about me. My education background. I had my Bachelor of Science in Physics from Taisholari University of Education, Ijebode, Ogun State in Nigeria, where I had a first class in physics. And thereafter, I moved to Germany for my Master of Science in Photonics, which I got from the Abbey School of Photonics at Friedrich Schiller University in Jena, Germany, on Abbey School of Photonics scholarship. And afterward, I was able to start my career as a CS, which is customer support, competence engineer, focusing on optics in a small city of Veldhoven in the Netherlands. So I moved from Germany as a student to the Netherlands to start my career, and I was there for 2 years as optics engineer. And afterward, in 2024, I made a decision to transfer to the United States of America. So my company then was able to transfer me to one of our offices in the United States, and there I shift some focus from optics to reticle stage, which is also more of optics. In a few minutes, I will, in my presentation, I will explain to us what that means in semiconductor and what it entails more deeply. So that's what I've been doing to date. And here you see some pictures of me. Let me see if I can on my pointer because that might be useful. Do you see my pointer?
Yes. Yes. Yes.
Okay, so yeah, myself, the typical day in office in these two pictures, and then here in the clean room, I will also show us what a clean room looks like, what a fab looks like, and what are the actions in the clean room. So yeah, let's dive deep into the topic. So why semiconductor matters? What is semiconductor? So everything around us today that's digital, that's electronic, is really semiconductor. So semiconductors, it's powered smartphones, it powers AI, cars, healthcare. So everything in the world today depends on chips. Everything in the world today depends on semiconductor. So if you open even this as the simplest radio, so the simplest digital product, you will see chips in it, you will see panels in it, you will see PCB board in it. So the chips attached to this PCB boards are all kind of powered by semiconductor. So global economy depends on the chips, and chips are made from semiconductor processes. Optics is at the art of chip manufacturing. Most stuffs in semiconductor manufacturing is from optics. Optics is the physics that we use to make most of this stuff possible. Uh, to my next slide, I want to show us what the ecosystem of semiconductor looks like. The ecosystem of semiconductor is so wide. Not one company can do everything because you have variety of tasks to be done. You have variety of processes to be achieved. You have variety of steps to be done. So one company cannot do it, one person cannot do it. So it's really interwoven, and it is a chain of companies. Each of them doing their thing in a very excellent way. So here I have it that many companies, one mission, and they power the future. So what does the ecosystem look like? So, for example, if you look at the research, so the research STEM is like people discovering new materials, devices, architectures, like what are the stuff that can scale technology further? What are the stuff that can push technology further? What nodes do we need to develop? How do we make that possible? So example of the people who are involved in that is my company, for example, ASML. We are always driving how we can power the semiconductor industry with lithography. We started with PAS 5000 system. We moved to deep UV, which is deep ultraviolet region. When you are talking of like 135, 130 nanoseconds, nanometer region. And now we move to what we call extreme ultraviolet, which is what I work on, EUV, which is more of 13.5 nanometers. So you see that kind of shift, a shift of using a light of 135 nanometer to a shift of using 13.5. So these are some benefits to create powerful chips. So these are the stuff that we work on to research on how do we scale it even more further. We are in 13.5 today. How do we even kind of challenge ourselves to have more better products, more better EUV, more better lithography? So ASML research on it, Intel works on it. We have IMEC. IMEC is also a very good company that's also researching on lithography. How can lithography be better every day, every now and then, and every year? So these companies, they make equipment. They make equipment. For example, ASML makes lithography equipment. So these companies make metrology equipment and all equipment to make sure that we push this technology further. And when you leave the research part or the equipment makers, you can come to the design. So for every chips needs to be designed. You don't just make a chip because you want to make a chip. You have to make a chip for a particular purpose. You have to make a chip with a design in mind, with a goal in mind for what that chip is going to solve. So how powerful you want that chip to be, and what problem you want it to solve. So that's where company like Nvidia comes in. So Nvidia customers, they make they design the chips. Intel also has some branch of Intel, like a branch of their business that's also designing chips. So they enable companies and IDMs to create chip design and validate it. So once this people make the design of what chips they want, then they send that to the manufacturers. So when you have the design of the chip you want to have, and so a particular purpose, then you send it to the manufacturer, and that's the third step. So here you have the manufacturing. So this is where they build wafers using advanced process technology. So they want to make sure that the chip design that NVIDIA is looking for example, we are able to print it. We are able to make it happen. And how do you make it happen? You have a wafer. So here you see this kind of wafer. I will show a small kind of video as time goes on. Here you have wafer and you see some images being printed on the wafer. So that's it. So you have images of what you want to achieve with the chip being printed on it, and you have companies like TSMC dominating that kind of industry. You have Intel also. Some part of Intel is also doing this, that they are manufacturing chips for cheap customers. So here you have foundries all over the world. So they manufacture chips on silicon wafers, and for you to print image on the chips, then that's where you need ASML. For example, the company that I work for, you see, this is just showing an illustration of ASML system printing on top of the wafers. In a few minutes, I will come to more detailed explanation of this process. And when you have the manufacturer manufacture the chips on silicon wafers, then it goes to the packaging. So packaging is where you then break the silicon into units, and that's when you can have all this. You have it singly. So they assemble the interconnect and everything. They make sure the die is fine. They test it. So here you have TSMC working on it. Intel is also having packaging departments. You have Amcor and other technology companies. So they bring the chips to life. So they make sure it's tested, it's validated, and everything really works as expected. And when you have the chips then finalized by the packaging companies, then it becomes a product. It becomes a product that data center can use. It becomes a product that automotive industry can use, that mobile industry can use, that anybody can use. So that's when you can say, yes, you have a chips in the car, you have a chips that's powering Tesla, you have a chips that's powering a kind of a HP laptop, a kind of Apple laptop, So that's when you have AI data centers and everyone using it. So that's like the end product. Then it comes to the customer, which is the end product. So for you to have a product that you can use in any technological build up, it goes along a chain of process. And yeah, in my presentation, I would like to enlighten more on that. So you see, it's not something the company can do on their own. Semiconductor is so wide, and whatever you are doing in semiconductor field is relevant because you're doing your own part and you cannot do everything. So that's why it's also a very big field that you cannot understand everything. You can only understand what you are doing and your own part. So to position yourself as engineers in Nigeria is really very good field because there's a lot of opportunities for you. There's a lot you can do in this field. To my next slide, I want to give some brief explanation of semiconductor manufacturing. So here I say that lithography is the most optics intensive step. So lithography is where ASML comes in, and I will explain it in a minute. So this is the most optics intensive step where microscopic circuit patterns are printed on silicon using light. So we use light to print patterns that we want on silicon wafers. So what do you have? You have wafer preparation. So this is an example of a wafer. So this is a kind of a finished wafer. So you have a wafer that stuffs are not printed on it, and you have to prepare it in the fab. In a minute, I will show us a video of what the fab looks like. You prepare the wafer, you create a thin semiconductor substrate on it. It goes through oxidation. Then when it goes through oxidation, then you can print a pattern of the image of the chips of what you want it to achieve. With light, you use it. So this is where ASML comes in. You can print the patterns on the wafer, and after you print the pattern, it goes through etching. So this is where you remove some materials that are not useful on the printed stuff. Then from etching, it goes to test, where you have some electrical and functional testing, and the test continue to CMP formation of metal, metallization, CMP, ion implantation, to all just make sure that you have your desired image, your desired pattern on the wafers. So this is just like the chain of the semiconductor process in the fab, in the typical fab you see. So this is a video I want to play on what a fab looks like. I hope the sound can come out, but yeah, let's give it a try and see if we can have the sound. I'm trying to see how I can play this video. Let me see, pointer option. Let me see. Okay, yeah, I have it.
Trying to manufacture something that nobody else in the world.
Are you able, guys? Are you able to hear the sound of the video?
You can hear the sound.
Okay, good, perfect. So yeah, let me just continue with it.
Trying to manufacture something that nobody else in the world is able to do, and so every day we're doing things that we've never done before. I spend most of my mornings in the clean room. It's the best place to be for an engineer because that's where everything is happening. That's where we're actually making our chips. In the semiconductor world, smaller is better. For 14 nanometer, we're looking at a ultra low power device. Everything behind our technologies, you make it smaller, you make it faster, and you're able to use a lot less power consumption. 2 technologies ago, we used human blood cells as a measure of how big our transistors were. If we look at a transistor, like a gate length now, we're on the order of like 30 atoms. It's really small. There's not much else to compare it to other than an atom.
It's the most sophisticated manufacturing process in the world, and it's probably the most automated manufacturing process in the world. And so that in itself is challenging. We're always on the cutting edge. Our wafers are 12 inches in diameter, and we move 25 of them at a time in a box. And it just weighs too much for one person to do repetitive moves, so we had to automate it. When we talk about the vehicles, it's part of our AMHS system, our Automated Material Handling System. It's the transportation vehicle that picks up the product and delivers it to the process tool. It takes it from the process tool and delivers it to the next process tool. If the tool's not ready, it puts it in a storage unit. We keep track of the priority of what needs to move where first. We know where all the product is in the factory at any given time. In the old days where automation went down, it probably wasn't as important. The factory still ran. But today, if major parts of our automation system goes down, the factory stops. I think what excites me about what Intel does is the computing capabilities that we make possible that make people's lives better and more enriching.
So that's a very short video of inside the fab and what it looks like. So in that video, you can see that there's a FOUP moving. So the FOUP is containing silicon wafers. So a FOUP can contain like hundreds of silicon wafers, and you see that moving from one system to another. It's moving from one machine to another. It takes it to the machine of etching. It takes it to the machine of to the system that's doing the lithography, for example. It takes it to the system you're doing a lot of processes from the beginning of the semiconductor process to the end. And that's what you have in the fab. So once you have everything printed, then it can go to another customer who is packaging it. So that's a very interesting clean room. It's a super clean room. You have to be so clean because you don't want to introduce any contamination to the chips or to the wafers. And in a minute, I will also talk about some challenges we have in working in a clean room. So contamination is a very big factor. It's a very, very big topic. So you want to avoid it. So it's all automated. So the system is not something that a woman or somebody can be carrying the FOUP of the wafers everywhere. So it's all automated. When you enter your fab, you see the FOUP moving on top of your head. You see it moving everywhere. It's all automated. They know where to go. So they are moving silicon wafers from one system to another. It's all be automated. So this is a kind of scenario in a typical fab. And I want to then go into EUV lithography. So this is really what I do. This is where I come in, and this is what my company does. So when we say EUV lithography, what does it mean? What is happening? So in actual world, what we have, before I play the video, I'm about to play a video, but before I play a video, let me try to create a scenario on top of our head. So you have a pattern you want to print on the chips. You want to make for chips. So you have some pattern, some image, and you have that image somewhere, and you need that image to be transferred to the top of silicon wafers. And you want that to be done in many steps as much as possible to give you the best resolution, to give you the best image as much as you can have. So how do you transfer that image from, say, in a drawing, for example, or say an image is described in a metal? How do you transcribe, or how do you kind of transfer that image in the metal to silicon and make it really work the way it should work, to transfer it electronically? So that's what lithography does. So lithography is a step, or is a machine, or is a process of we trying to make sure we have some light, guiding some image of an object, and transferring it to the top of the silicon wafers. So how we do that is a really enormous engineering, and I want to play a video for us here that shows what are we doing. So for EUV, the light you are about to see is a 30.5. Let me on my pointer back. The light you are about to see is a 30.5 nanometer wavelength light, and it's a vacuum environment. You have reflective mirrors from Zeiss, also from other suppliers we have. And with this kind of technology, you can have advanced node of 5 nanometer, 3 nanometer, and etc. So we can deep dive into the video. I hope it plays. Let me see how to. Okay, I have it. Are you guys able to see the video?
We did. We saw it.
Yeah. So that's a typical process of lithography, and I will try to explain it with this slide. So what did you see in that video? Let me on my pointer. Sorry, this pointer. So this is a typical EUV system of ASML. What is happening? Let me try to explain. Here is what we call the source. So here you have what we call source light. So this is source laser. And here you are perpendicular to this angle, you have something we call a droplet generator. So you have a generator creating some droplets of thin plasma. So when you have a droplet generator creating thin plasma, and you have a laser, if this laser of certain frequency, if this laser hits the droplet generator, the thin droplets being generated, it creates EUV that we're looking for. So people ask, how do you create EUV in a vacuum system? So the way we create EUV is to have a very super high laser of certain frequency. So when you have that high laser and you have a droplet generator of thin plasma being dropped per seconds, then you have, when the light of the laser is hitting it, it creates an EUV. And when you see from here, so let's move from this source, EUV light is created and it enters this mirror. So this is some mirror guided pathway from Zeiss. It enters this kind of vacuum chamber. This is what we call the illuminator. So if it enters the illuminator, here you have more than 1,000 mirrors. So there are more than 1,000 mirrors on this surface. And from this pupil facet mirror, it shapes the light. So the light of the EUV coming from the source in the illuminator, it comes to the facet mirror of like 1,000 mirrors, and it shapes the light in a way that we want it to be shaped. So we control that for each product. And when this shapes the light, it comes out to this type of mirrors, and these mirrors also kind of shape it in a certain way, and that is transported in certain vacuum chambers to this reticle stage. So I said earlier, when I was in the Netherlands, I was working with this regime. I was working on everything that happens in the illuminator. And what you have here is reticle stage. This is what I work now. So what is reticle stage? So reticle stage is like the stage holding the image of the customer. So this stage is where you have the image you want to print on the chips. So this is the wafer. So this is the wafer stage. If you see my mouse. So this is the wafer stage. So here you have the silicon wafer, and you want to print certain image on the silicon wafers, like the video I just showed you. So you place the image so automatically. So this is not something you use your hand to do. Like everything is automated. So the image of the customer that you want to place, that you want to print on the chip or on the silicon wafers, is placed on this reticle stage, and there's a way this reticle stage moves to make sure that the light coming from the EUV hits that particular image on the reticle. So we call it reticle. So this light must hit that image on the reticle. So when it hits it, it's like copying it. It's like taking that image. So when it takes that image, this is what we call the projection optics box. This reduces the image. It shrinks the image in like 5x factor, because the image you see here is very large, it's very big. So this mirror here, the projection optics box you have here, the intention is that when the light has taken the image from the reticle stage, the image then comes down, and this mirror helps to reduce the size of that image, because you need that size to be reduced before it can be printed well on the wafers. So that also happens in the vacuum chamber of the projection optics box, and you finally have it being printed on the silicon wafers. And this is happening, you are doing like 100 of silicon wafers per second, for example. In the last video, I think they showed that value. So this process is so fast that you are having like 100 of this process being done in the seconds. It's a very fast process. Excuse me. It's not something that you can do by just manual stuff. It's all automated, and every second this system needs to keep running, because in each fab, customers are printing silicon wafers, millions of silicon wafers every day. So every day, customers are printing different pattern on silicon wafers every day. So this system needs to keep working. This physics needs to keep happening. This engineering needs to keep happening every seconds. Every seconds, everything must work fine. So we have to control the temperature of the mirrors. We have to control the contamination, because here, you believe with me, if you have mirrors here and you have EUV light, a very powerful light, hitting the mirrors, so this could lead to deformation of materials. So some of you are material engineers, you know what light can do to a material. So when the light is hitting the mirrors, there's a lot that can happen. Contamination can happen. You can say the material of that mirror, shedding particles, or kind of losing resolution over the time, or losing the standard over the time. So we try every best every time and every now and then to make sure we maintain the quality of these vacuum chambers and the mirrors, to make sure everything works perfectly. So this is the challenge of EUV lithography today, to make sure this process keeps working and wafers can be printed many layers per few milliseconds, for example. So you have to make sure this keep running for multiple systems, and this system are not going down. So my role as a CS, or as a customer support engineer, is that for every of the system we have in the field, my role is to make sure that this stuff is working fine. So now I'm working on the reticle stage. So there are a lot of factors. There's a lot of sensors we have on this reticle stage. There's a lot of vibration going on. There's a lot of mechatronics. There's a lot of mechatronics on this reticle stage to make sure we have the right light system. So my aim is to make sure this stage does not fail. So my aim is to make sure everything that's happening on this top module is being done right, and there are no disturbances, and it's not leading to a situation where we have a wrong image. Because mind you, if there's a wrong image, or if this process deviates, so if there's a deviation in this process, you will have a wrong image at the end of the day. And if you have a wrong image on your wafers, by the time it gets to the testing, it will be revealed that these wafers are bad. And if a wafer is bad, guess what? It becomes useless. So customers are wasting millions. They will waste those wafers. So those wafers become useless. They cannot do anything. You cannot do anything with those wafers. So that is why it's very critical for engineers to make sure this process works so perfectly, so that at the end of the day, you have wafers with the right image. You have millions of wafers per day with right image. And if there are anything we need to do to maintain the system, to optimize it, so this is the engineering of light. This is the engineering, this is the challenge I go to work daily to try to solve. So this is really the engineering of EUV. So EUV lithography is when you have a source that is generating EUV light, going through some certain mirrors to kind of have some pupil shapes, and collecting the image of the customer of the reticle from the reticle stage, and then shaping the light in a certain way, and copying it on top of this silicon wafers. So at the end of the day, you will have you have the silicon wafers being transported from this stage, from this wafer stage, out of the FOUP. And that's the stuff you see earlier in the video I played for the fab, that the stuff are moving on the top of the crane. They are moving on top of the building in the fab. So this is going out and it's going to be stored. And once that kind of FOUP, we call it a FOUP. So FOUP is like a big package that is collecting silicon wafers. So once it's full, the process is done, it takes it to the next machine for next process. So this process needs to keep going on every second. As I'm speaking with you, more than, I can say, a lot of numbers, hundreds of systems are in the field running every seconds, generating money for the customer. So this is the ecosystem for semiconductor. This needs to keep happening for you to have faster computers, for you to have AI, for you to have faster cars, a lot of stuff you can do with chips. So for you to have a chip that is powerful, you need this EUV lithography. And today, ASML is the only company making this EUV lithography system. And with EUV lithography, you can make more powerful chips. Someone can ask, why do we have to use EUV? We also have what we call deep ultraviolet. That's DUV system. So DUV is not using a powerful light. It's using something like in the range of 130 nanoseconds, a nanometer. And with that, you can still achieve it, but it's not going to be powerful. Your chips are not going to be powerful like having an extreme ultraviolet light that EUV gives to you. So these systems, they cost a lot of millions of euros or millions of dollars, but because this process is very critical and it's highly sophisticated and technical. So what are the challenges in semiconductor manufacturing? As you already can guess, from the process I've just described, there will be a lot of challenge. And that's what we try to solve today, every day as customer support and as people in this field. So I have heard that from design to volume production, multiple complex challenges impact performance, cost, and time to market. So, for example, you have the process complexity. The process is too complex. It's too complex. A mistake in one process will lead to rework of other processes. A mistake in one process will lead to bad job of other processes. It will kind of render other processes irrelevant. So that's why you have to make sure each process is correct and each process is right and true. So one of the big challenges is maintaining the complexity we have. How do we maintain standard with the complexity of this process of lithography? So you have increasing number of fabrication steps and tight process control. So these have to be controlled to make sure you have good wafers at the end of the day. So What you also have as a challenge today is what we call yield management. Any small defect or progress variation, as I said earlier, will lead to issues on the wafers. So we have to make sure the yield is managed and everything goes out fine, so you can have best yield. Because the better your yield on the wafers, the better the performance of the chips. And here you have the fishery scale. So manufacturing increasingly smaller transistor structure. So there's a scientist, there's a man they call Moore's law. So there's a Moore's law, and what Moore's law is saying is that every 2 years we should have chips that are becoming more powerful and that are becoming more congested. So you want to package more chips, more chips in the transistors. So you want smaller transistors but very powerful. So it's like making something more smaller but becoming more powerful, like double the size, double the size of or like the scale of its power. So this is something that is really difficult. So that's what we call fission scaling in semiconductor. So all this have to happen to make sure you have the best chips at the end of the day. So supply chain dependency. So as you know, I've talked about like 4, 5, or 10 customers involved in this ecosystem. So each customer needs to be there. So the supply chain to make sure there are materials, that equipment needed for each of this process is very, very delicate, is very, very complex. So supply chain is really needs to be optimal for you to really succeed in this field. Contamination control, I've spoken much about it, that any contamination on the wafers, we yield it all useless. So we try to make sure the material are not generating particles, the materials are not generating contamination. This is very delicate, this is very kind of challenging, but this is something you have to make sure to do, because any kind of contamination on the wafer surface renders that wafer useless. And if it's useless, the customer is losing millions of dollars. So you have power and thermal challenges in chip production. So this is really very big, because you need more water, you need energy to make all this happen. So this is a very big problem. So advanced packaging integration, scientists are always working on how do we package more chips to make it more powerful. So this is also a big factor for the people involved in packaging. So capital intensity. So someone was asking me some time ago that, hey, can Nigeria also kind of create a semiconductor hub? Can Nigeria also make lithography, for example? This field or this kind of industry is not what a country that is not so strong financially can just do. This is an industry that needs conglomeration or coming together of countries that are really heavy financially. So this is not something somebody can just do and say, hey, I have some money, I want to create a semiconductor company. No, it's so capital intensive, and that's why you don't have many companies doing it. You don't have many countries investing in it, because it's very powerful. It's not something you start in the 5 years and you're already making products. This is a step, or this is a process, lithography especially, that can range for 10 to 20 years before you achieve anything. And in that 10 to 20 years, you have invested billions of dollars into it to make it happen, because it's a very critical field. So it's capital intensive. So it's not something someone can just wake up and say, I have an idea I want to do. If you have an idea, the best thing you can do is to go apply to a job in one of the companies doing it and let them employ you. There you can practice your idea. But saying that you have an idea, you want to create a company, this is not the field for it. This field is too difficult for it. It's too capital intensive, So process variability is also one of the challenge. Technology transition risk is also challenge, because I talked about DUV. Now we have EUV. Now we just launched our INA, high numerical aperture EUV, and Intel, I think 2 days ago, they launched a new stuff they just made, a new mode they just made with our INA EUV, a very powerful chip that they just made with INA system. So this is also something that is a challenge. How do we scale technology? How do we make sure we are producing more powerful technology every now and then? So these are one of the few challenges we have in the field today. So also metrology and inspection. This is a very big topic. So metrology is something big. Metrology is when you are trying to measure the light behavior on your wafers and everything, controlling the lights to making sure that it works the way it should work. So you are measuring future, you are inspecting it, you are looking for defects, you are using a lot of sensors. So if you are interested in building sensors, this field is for you. If you love to work with sensors, this field is for you. So there's a lot you can do. Interferometry, if you love to build interferometers, this field is for you. A lot of stuff you can do with imaging system. You see this just a typical lab in one of our office. So you have a lot of optical systems coming together, being formed together for research to create, to mimic what we have in the fab and to really advance technology. So metrology is very important. Inspection is very important in this field. So how does this affect you? What are the opportunities for you as young engineers? So as young engineers in Nigeria or all over the world, there's a lot of career opportunities in semiconductor that you can do. You can be a photonics engineer, you can be an optics engineer, chip engineer, process engineer, packaging engineer, various roles. So you have a lot of stuff to do, and all skills are needed. So you need Python skill, simulation skill, data skill, communication skill. Every skill you can think about is all needed in this field, and the opportunities are global. And if you want to join the ASML, for example, you can connect with me. But there's something I like to tell people: this field is highly regulated. It's highly regulated by the government. So because of that, not all countries can really easily access this technology. So the EUV technology is controlled, is government of America controlled. So I tell people, if you want to enter this industry, it's difficult to enter it if you're in Nigeria. So if you're in Nigeria, one of the way I usually advise people is, number one thing, try to get out of the country. If you want, try to get out of the country, maybe on a scholarship. For me, that's how it happened for me. I got out of the country to Germany to study for my master's, and from there I was able to stand a chance to enter this industry. So for most young people that want to enter this industry from Africa, my advice is always try to get out of that country. Try to get exposure. Try to go to countries where research are really more funded, really more intensive. Go to countries or go to labs where you can have materials, where you can learn, where they can train you to be an engineer, where they can train you with state of the art equipment, not just equipment of 10 years ago, of 20 years ago. Go to countries where you can have state of the art equipment, where you can gain the state of the art education and knowledge. And that might need you to leave the country, Nigeria. So most of the time, I tell people seek scholarship. If you graduated from university, if you graduated well with good CGPA, try to seek scholarship abroad from a master's or for a PhD. And when you seek scholarship, there are a lot of companies in this field offering internship for students. So you can do internship with companies. From there, you can get the job. You can apply to them, and you can really, finesse your profile. So it's really difficult, unfortunately, to enter this field from Nigeria because there are no players of this industry in Africa. So it's not even only in Nigeria, but in Africa generally, there are no players of semiconductor in Africa. So if you really want to practice it, you have to be open to relocation. So that's the big challenge about this. But yeah, it is possible if you move out on the scholarship. If you work hard for it, you can gain international scholarship. It's not easy, but if you can work hard for it, you can connect with me on Twitter. You can connect with me on LinkedIn. We can walk through it, how you can gain some scholarship. And if you have some scholarship abroad, if you move abroad on scholarships, you stand some chance to enter this field because there is a lot of opportunities in this field. There's a lot to be done. There's a lot you can do. You will be trained and you will work on it and you will succeed. So this is a field that's really promising and it's a field that will always be there. This field has been there for since life immemorial. So it will continue because chips is needed. We need technology. Technology is not going anywhere. AI is needed. It has come to stay. So you can position yourself. And to position yourself, you need to seek for global opportunities, seek for global education, and I can only wish you success in that. So in conclusion, semiconductors, it powers the world we have. The world we live in is powered by semiconductor. Everything in the world today is digital. Everything is digital and it will always be. It will continue to be. So chips have come to stay. They will always be useful. They will always be needed in the world. light drives the modern technology, and there's huge opportunities ahead. Huge opportunities beyond what we can talk about. There's a lot of roles you can do. There's a lot of opportunities for you. You just need to key in. You just need to be in the right environment, and you can enjoy it. So that is what I have for you, and I will be open to your questions. Let me stop sharing.
Thank you very much, sir.
It's my pleasure.
This wonderful. Let me turn on my video once more. So, I'm really fascinated. Like the whole semiconductor stuff, it feels like serious magic. Like how
Yeah,
how are we able to how are we able to use technology to use stones, sand,
yeah,
basically to
yeah.
control technology. It's very fascinating.
Even we that we are in is day, like anytime I have chance to go to customer fab like Intel. A few months ago I was in TSMC in Arizona, in Phoenix, in America, and I was just amazed. When you go to a fab, you see the systems, how everything is working, and the stuff that they are able to make, you feel like, oh my god, how is this happening? So it gets so crazy. Even what you are also working on is, you can't just think about it. It's too crazy. It's just too crazy. It's a really fascinating feat, and I love it. Yeah,
I'm very grateful for your talk. So we have some questions. Yeah, if you also
okay.
have any question that you want to maybe speak, you can just indicate. I will unmute you from my end. But I have some questions already written down in our chat, so I'm going to speak. I'm going to read them out.
Yeah,
So, first one from Heidu Melchizedek. Is it possible for the machine to make errors? I think he was he's referring to the video of that machine.
yeah.
What's the machine again?
The,
So
the
he's
EUV
asking if it's
EUV
possible.
lithography machine.
Yeah. So is it possible for the machine to make errors?
So I want you to understand something. Any error today that we talk of and we say it's machine error is not machine error. Error is from a deviation in the process. It could be a software issue. So it could be a software hiccup. It could be a material malfunction. So when your material is, for example, misbehaving, because when you are designing that material, or when you are designing that stuff, there are some stuff you didn't put into consideration as an engineer, because as an engineer you don't know everything. In while you are defining your requirements for any engineering process, you don't have 100% idea of stuff you are designing for. So in any requirements you are writing as an engineer, you don't have 100% uh, foresight into how it will behave when it gets to the environment that it needs to work in. So you are learning every day. So when you make a design, you put it on the system, on the machine, it starts to behave, then you learn from that behavior. Oh, this stuff that we made, or we made this software, we made this software patch, or we write this code to do this stuff in that machine. Oh, the software, when we install it, we start to see this issue. Oh, after 3 months, the software starts to have some hiccup. So that's what today we say machine has issue. So it's not really basically the machine having error, but it's because of the limitation in the design, the limitation in human knowledge. So the human is the one that made the machine. So if machine is having error, it's because the design of the designer has not put into account everything he needs to put into account. Or maybe there's a new introduction into that machine that is conflicting with so for example, your laptop, sometimes you get a new software, you want to install a new software on your laptop, and you install that software, and maybe that software then make your laptop to misbehave, and you feel like, oh, maybe this software is too bigger, maybe the memory is consuming all my memory of my laptop. So there are some software that will take, that needs 4 gig RAM, for example. So your laptop is 2 gig RAM, and there are some software that they can only thrive in the 4 gig RAM laptop, in 8 gig RAM laptop. So you as a person, as the owner of a laptop, you know your laptop is 2 gig RAM, and you have gone to get a software that are so powerful. I can't even remember any software on my head, but there are a lot of software that are powerful that can only survive a 4 gig RAM laptop, and you install it on your laptop. How will that laptop behave? It will start hanging. So after a few times, you will see that your laptop starts hanging, and then you try to say, what's wrong with my laptop? Nothing is wrong with your laptop. It's just that you have introduced something that you did not, first of all, think about the memory of your laptop. So before you introduce something new into an environment, you have to think of other dependencies. This software I want to install, how many memory will it consume? Do I have enough memory on my laptop? So the same thing in engineering. Oh, I want to introduce this stuff to this machine to improve the performance. If we introduce this material, if our system is having, for example, hydrogen gas. So let's say, for example, you manufacture a piece of hardware. Let's say you manufacture a piece of hardware like this, and it's going to maybe help the light in the system somehow. And this hardware is being made by, let's say, zero dot particle or titanium particle. But you, as an engineer, you didn't think that, oh, our vacuum system, sometimes there's hydrogen gas, sometimes there's nitrogen gas. And have you thought about the impact of nitrogen gas on the material you use for your design? So sometimes the impact of nitrogen gas, maybe this material that you have used titanium for, maybe after 3 years that is being exposed to nitrogen gas, maybe it will start to shed particles. So those are the considerations. It's just to say that any error you see on system, on machine, is human error. Somebody didn't think about it. They thought, it will not be a problem. No, that material is fine. Even if hydrogen gas is eating it every day, it will be fine for the next 20 years. It's a lie. But it's due to the limitation of somebody. So somebody designed a software, write some code and say, this software will do this thing. But the reality is that software maybe is missing something. And at the end of the day, it fucks up and we say, oh, the system is having an issue. So in natural sense, machine having error is meaning that humans that design it are having some limitation. That would be my answer.
All right, thank you very much for that. So the next one, I don't know if you want to unmute himself to say it, or let me just read it.
Okay.
What are the tools you use in your day-to-day tasks, software and programming languages? So
Yeah,
your
so
software and programming languages.
yeah, there's a lot of software you use because there's, even in ASML, there's a lot of departments. So for me, my department is more of customer support. So there's an issue happening on our systems worldwide. I have to diagnose it to see what is the issue, how do we resolve it. So it's different from someone designing. So I have colleagues that are designing mechatronics, that are mechatronics engineer, that are designing. A software that a mechatronics person is using is different from software that an electrical engineer is using. I have colleagues that are electric engineers. I have colleagues that are, name it, chemical engineers. So I have colleagues using, different microscope, TEM microscope, same electronic microscope. So they have different software, and we also have inbuilt software from our companies that we use. So, but for me, it's mostly of MATLAB. So what I use most time is MATLAB to run some traces, to plot some graph. Python is also very good. And so apart from MATLAB, Python is just mainly on system diagnostics tool that our company has made. They're all internal. But yeah, majorly what you can learn as a tool is just more of Python, MATLAB. And if you're an engineer that designs, then you want to learn about designing principles and designing softwares. Yeah.
Right. I think that answers. And the other question says, which company or process makes the wafers themselves? When they say when they say there's chip shortages in the world, which of these ecosystems usually cause that?
So if there are chip shortages in the world, it's because there's always more demand than supply. So it's not necessarily one company creating the issue. So for example, today, so let me give you a scenario. For example, today, what are the companies making chips? that owns foundries fabs. So you have TSMC, you have Intel, you have Samsung Electronics, you have SK Hynix in Korea, you have Micron. So each of these people, they already have customer. So TSMC, for example, Nvidia is their customer, Apple is their customer. So Apple already has some stuff they want TSMC to make for them. Nvidia is bringing order, but the reality is TSMC is also, maybe they have 1 million employee, for example, or maybe they have 1,000 system. But the reality is that system is also not enough for them to supply everybody what everybody needs to have in a day or in a week or in a month, for example. So you need to scale, you need to become bigger. So that's why now TSMC from Taiwan, they have come to build fab in America. And now, yesterday or 2 days ago, they announced another 100 billion investment in America. They want to build more fab because the reality is there's always chip shortage. And that's why each company, they are trying to expand. Samsung now in Korea, they've come to America now in Texas. They've built fab in Texas. Now they are building one in Taylor in Texas because everybody, they see that there's need for more. So now you see this guy, Elon Musk. I don't know if you found it in the news. Elon Musk also now, because of shortage, is going to build his terafab. So it's like, instead of me waiting and queuing behind Nvidia, behind Apple, why don't I also make a fab? So it's going to make the biggest fab in the world. So that's the thing. So it's not about one company creating it, but it's because the demand are so high and company needs to keep expanding. And for example, most companies rely on ASML for EUV lithography. So we have to keep producing system every day. So every day we are shipping. Now there's a plane in the sky carrying ASML system to somewhere. And for one system, you need like 4 planes to carry it in ASML. So 1 hour EUV system, when you break it down, you need 4 planes. 4747, Airbus 747 to Boeing 747, I mean, to carry it. So that is happening every day. So we are making new system every day. Now I'm talking with you. I have colleagues in the fab working. I have colleagues in the industry in the clean room making new system. So the demand is so high that it's not that one company is the one causing the issue, but it's just they just need to keep expanding. So now ASML is also expanding. So that's why we need more people. We need more employees. You see them, you go online, all semiconductor companies, they are all hiring. They need more people. They are expanding. So it's all ecosystem of all companies, not one company causing it.
I think that answers his question. And maybe can you answer his first question was which company or process makes the wafers themselves? So like the raw wafers. Can you give us an example of a company that makes?
So you mean what do you mean by so the silicon wafer?
Yeah, the silicon wafer.
Those are really suppliers that are not really popular. So I really don't know any supplier making it. Or the major players are the ones I know that hey, when you have already wafers, then it comes to our system. We print on it, and it goes to Intel and other people that they make chips in on it. They're like they do the packaging, they do the testing and blah blah blah. So but we have millions, or let me say thousands of suppliers doing all these small processes, but they are not as big as the big players. So I really don't have a name on top of my head of who are the one converting sand to silicon, because I know that's the intention of the question. So I hello. Hello.
My network failed me just now.
Okay. Yeah. So I tried to answer that question. Yeah.
Yes. I got it. So I don't know. We still have some time, and we
Yeah.
still have some questions. So this is more of a personal question. I am passionate in robotics, PCB, and circuit design. What are my chances to work at ASML? Can I get a path guide
Yeah. We
to
have
that?
robotics
I
engineers in
think you've
ASML.
really explained more about that
Yeah,
already.
we have robotics engineers roles. PCB, we have electrical engineers also that are designing PCB, that are making stuff. So all this stuff are also circuit design is all possible. But the career path, like I said in my talk, is difficult if you're in Nigeria, to be sincere with you. To be sincere with you. I'm not saying you cannot apply for ASML job from Nigeria. You can apply, but sometimes they don't want to sponsor someone from Nigeria. They don't have time to wait because it takes a lot of process to sponsor someone from Nigeria. They don't have time to wait for 1 year before that person resume. They don't want to wait for 6 months. When there's already, so for example, you are in the Netherlands and there's a role for this design role or something, and they post the job. So in the Netherlands alone, maybe there are 50 people that have already applied for that role in the Netherlands. So people that if you tell them, can you resume in the next 2 weeks, they will say yes. They don't need visa. They are already citizens of the Netherlands. So and you are now in Nigeria, that you need visa, you need everything, that they need to sponsor your visa. And in sponsoring your visa, it will take like, let's say 4 5 months or 6 months. So most of these jobs, they are so critical that they really don't have time to waste and say, hey, because this talent is from Nigeria, unless you are so special or you are so good. And to be frank with you, this is not to like abuse any company or any school. The education you have in Nigeria for most of this stuff, they are not something so competitive, in my opinion. So you don't really stand a very bright chance to defeat an applicant who is applying from Europe, from top university in Europe, for example. Somebody has gone to university in Germany, and you are from my school, my tertiary university of education, for example. It's really difficult for you to beat them in interview. So for them to say, we have to go for this Nigerian guy. So if you are good in Nigeria, use that your brilliance. This is my advice. This is what worked for me. Use that your brilliance to enter Europe or to enter America as a student. Go to that school and prove yourself. Learn stuff from top universities in the world. And if you can prove yourself there, then it becomes so easy for you to enter semiconductor field. That would be my advice, to be sincere.
Okay, so
Yeah.
that's very, very good advice actually. The next is what are the influences of AI on your day-to-day workflow, especially in the engineering part of things?
Yeah, AI is a tool that we are using, and we are investing on it also as a company. So for me, I don't use it in my day-to-day activity, but I have some colleagues that they rely on AI, some AI tool that they are using it for some we call it predictive monitoring. So some tools, some guys are using it for some predictive monitoring, but I don't use it personally. So I don't know the full scope of AI in my company. So because we have a lot of departments, so I don't know what all departments are doing. So, but in my own personal day-to-day workflow, I don't really use AI that much.
Okay.
Yeah,
The next one has already been answered. It's also asking how can an average Nigerian break into the field?
yeah.
Um,
I
so
know it's so difficult. You can
yes.
keep applying. You can keep applying. So let me give you a story. There's a Nigerian guy. There's a friend of mine. Last week, he had an interview with ASML in the Netherlands, and the guy is in Nigeria. He had an interview, and I think they like him. They want to go for him. But you know his issue. The guy was above 30 years of age, and there's a law in the Netherlands or in most of this country. If you are above 30 and they need to sponsor you, they need to sponsor your visa, there's a salary that the government has put as minimum. So normally the scenario is this: if you want to hire someone for this role, let's say this role is like $100,000 per year, and in the Netherlands, you can already around you in Europe, you can already have people that will apply, but the government will say if the person is already 30 years old and the person is from outside this area and you need to sponsor work visa for this person, you must be offering minimum of, let's say, $120,000. So that's just an example. So that my guy, after he did the interview, HR was telling him, you did well, but we cannot employ you because the salary, the minimum salary expectation for your age and for the because you have to do your visa is too high for this role. So I think that, let's say for example, maybe that role is going to pay 50,000 euros per year, and the visa office already say to employ this person since he's already 30 years old, you must give him 65,000. If I'm a business owner, what do you do? So I was like, I was even telling you, they were even good to tell you the reason why they will not employ you, because you're already 30 years old. And because that's the thing, if you are 30, if they are employing you from abroad, there's a condition from the government. And if you are already 30 years old, there's additional condition. So these conditions make it difficult for company HR to say we want to hire you from abroad, unless the role they are hiring for is an expert level role that they can pay that high money for, and they really struggle to find talents around them. So that's when they can say, let's make exception. Oh, because this guy is good, because we love his profile, we can pay him that money. And that role also is a very kind of specialized role. But if it's just a simple role that they can find other people if they want, they will not really, and the government is saying you have to pay times 2 of that money to get that person from Nigeria, they will not do it, unfortunately. So those are really the struggle.
Okay. Oh, it's really sad.
Yeah, it's sad, but it is what it is, right?
Yeah, it is. So there's a question here on: are there internships, research opportunities, or graduate programs you will recommend students to keep an eye on?
Everything is outside. It's all rely on you living in Nigeria to be sincere. Maybe in Nigeria now there are some, I heard of some cheap stuff in Nigeria ongoing, some school having, but I don't have the full picture of them. So maybe now there are some companies in Nigeria that, or in Africa, that can help you as internship in this field. I really don't know, because I'm not into chip design. So what I'm doing
Yeah.
is semiconductor, but it's far away from chip design. So if there are some stuff already you can do in chip design in Nigeria, I really can't say. All my knowledge is really more of companies already in abroad, that when you are a student in university, you can apply to them for internship. So if you're in America, for example, I have a lot of people from universities doing internship in my company. So if you move to Germany, for example, there's a lot of company in Germany having internship for students in this field. So those are the ones I know. But if you're in Nigeria, I'm not really too familiar, to be sincere, with what companies are hiring for this kind of thing in Nigeria.
Okay. All right. So then I think this should be the last question from here. So looking back,
Yeah.
what do you wish you had known as an undergraduate that would have made your path easier?
Well, to be sincere, I was lucky. I was very lucky. So I didn't struggle to get into this field. So it was not it was not it has never been challenging for me, or to get into this field was never challenging for me. So there was nothing that I would have learned that would have make it even more simple. So that's for me personally. That's for me personally, to be sincere. There's nothing I regret I didn't do, or that I regret I didn't know, because I was quite lucky with my school in Germany, with the opportunity. If you follow me on Twitter, you will have read my story multiple times where I try to narrate how lucky I was. So I would say I was lucky. So I didn't have to prove a lot of stuff. But yeah, what you can do as an undergraduate is to keep building yourself, keep learning stuff you can learn. Most importantly, keep your CGPA intact. So keep your CGPA intact, because by the time you are looking for international opportunity, the number one thing they are looking at is your CGPA. How good was this guy when he was in undergraduate? How intelligent is he? And the only way they measure intelligence these days is by looking at your results. So even if you are good, but your results are not showing if your results are not showing that you have a very bright CGPA, nobody will really easily believe you that you are good. So two advice: work on your CGPA. Secondly, these days what they also use is publication. If you're already an undergraduate, work with your professors, work with your lecturers, support them in their research, talk to them. try to make sure that if they are publishing papers, you are supporting them and they can include your name. I know most Nigerian lecturers don't like it, so they don't want to do it. But if you are lucky to have professors or lecturers you can speak to, like father to son relationship, please speak with them. That what can I do for you, sir? That's something I benefited in my undergraduate. By the time I graduated, I had two publications, one from my project and one from a lecturer because I just helped him to write introduction of his paper. He just gave it to me that, oh, I have this draft. Can you write the introduction for me? And I just sat down within a week. I was able to draft, I was able to read journals on that topic, and I was able to draft a one-page introduction. And he put my name. I didn't even ask. He put my name into the paper. So speak with your professors, speak with your lecturers. What can you do for them so that they can include your name in their publications? Because by the time you graduate and you already have one or two publications in your feed, with your name, even if it's 50 author, so far your name is there, you're also part of the co-author. So if you can have publications in your name, it will help you, because I can tell you the competition now for global opportunity is crazy. Everybody all over the world, or all over third world country, they're all looking for how to get scholarships. So it's now very difficult. So the only way now is to make sure your profile stands out. So CGPA, please make sure you work on it while you're in school. Building connection with your lecturers for publications, that's something I will really advise. Every other thing you can learn. If you don't know Python now, you can learn Python. To learn Python is, I learned Python in my NYSC. It was when I was doing my NYSC that I learned how to use Python. I didn't know Python before, by the time I graduated from my undergraduate. MATLAB, I think I used it for some time for my project, but Python, no, I learned it in my NYSC. These are the stuff you can learn when you sit down with your laptop. Within 2 weeks, you will learn Python. You will understand Python. Now, even with the age of AI, you can learn everything in a week. You can learn the basic stuff you need in a week. So these are the stuff that you can easily learn any point in your life. But what you cannot really rush to learn, or something you cannot rush to get, is something like CGPA, a very good CGPA, and publication history. So those are the stuff I will really advise you to work on.
All right. So thank you very much. So I have
Yeah, no
one last
problem.
question. Um, I have a background in materials engineering from Ghana. Can I apply to the same DAD scholarship you applied with my degree in materials engineering to break into the industry?
Yeah, one objection though. I didn't add my scholarship was not that, but yeah, I have a guy who recently moved to Germany on that scholarship. So yeah, you have materials engineering. These are the field for Germany. They love it. So you can apply for that scholarship. You can apply for Erasmus scholarship. There's a lot of topic for for materials engineering in Erasmus. You can apply for it. You can. It all depends on your profile. To be sincere, you can apply even to America. There's a lot of scholarships out there you can apply to. You can hit me up on Twitter, and you can. I can put my Twitter username in the chat, and yeah, if you send me your CV, your profile, what it looks like, I can give you some advice. And there are a lot of scholarships you can apply to. So I put in the chat my Twitter username. You can hit me up. Yeah, I may take some time to reply your DM, but yeah, one day or very soon I will reply you, and we can pick it up from there. Yeah,
All right. So Samuel Ashola is saying, I think he's working at Cheap Mango in Nigeria. I'll be happy if you can help us take this session with our interns at Cheap Mango. As it's possible, sir, we can talk more on this, please.
yeah. You can just hit me up with the invitation, and you can talk with you the same way you were able to secure my attention. So yeah,
Okay.
we can make it happen. Yeah, I'm open for it.
All right.
Yeah. Thank you all for
Is
your
there anybody
audience.
that
I
wants
really
to maybe
appreciate it.
talk, speak? Okay, yeah, well, good. So yes, thank you so much, Mr. Wale, for the time you
It's my
spent
pleasure.
with us today,
Yeah.
even with our African time. Yes. So we hope to from this. of people here. We hope to see some people that you might one day call colleagues.
Amen, amen. I pray so. I pray so.
Yeah.
All right.
So yes, we're
Enjoy your
done
evening.
with today's session. Thank you everyone for showing up. Yeah, you too. Have a nice day.